This is Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. Today, we are going to see how to use matrices tools while finding the solutions of linear systems. And this is an application of matrices for solving linear system. When we have set of linear systems, then we can able to find out the solution, common solution of all these set of linear equations by converting the given linear equations in matrix forms. The linear equations may contain n number of variables. Those equations first we need to convert in the matrix forms. So when we are converting in the matrix form, then the matrix will take in the form of AX is equal to B, where A is the matrix of coefficient, X is a variable matrix, that means containing number of variables which are there in the linear equations, and B is a constant matrix. So when we are while we are going to find out this linear solutions of linear system by matrices, first we can divide the given linear equations into two forms. One is homogeneous and the other one is non-homogeneous equations. So let us see when the linear equations are said to be homogeneous and when they are said to be non-homogeneous. Whenever the constant matrix B is not equal to 0, then it's called as a non-homogeneous linear equations. In the matrix AX is equal to P, whenever the constant matrix, this matrix is not equal to 0, then that type of equations are called as a non-homogeneous linear equations. They are linear since the power of each variable is 1. So whenever the power of each variable is 1 throughout the equation, they are called as a linear equations. So when these constant matrix equal to 0, we call it as a non-homogeneous equations. So you all know that in homogeneous equations, the power of each variable in each term are equal. For example, let us see, if you have 2x plus 3y is equal to 4, this is non-homogeneous equation. Instead of 4, suppose if you have 0, it is called homogeneous equation. Since the power of all variables in the equation is 1. So therefore, it is called as a homogeneous equations. So the method of finding out the solution for homogeneous and non-homogeneous differ by little bits. In few steps, they both the solutions of the linear system for homogeneous and non-homogeneous are differ. So let us see how to find out what are the steps involved in finding out the solutions of linear systems by matrices. In the given first step, the given equations have to be written in the matrix form. That matrix is called as AX is equal to B. Now, let us first consider how to find out the solutions of non-homogeneous equation. That is, when B is not equal to 0. When B is not equal to 0, how to find out the solutions that we are seeing it now. Now, for the given matrix form, the equations which are converted in the matrix form, first we have to take the augmented matrix, that is A by B matrix. That is nothing but the combination of the coefficient matrix and the constant matrix. Both are clubbed together. So if you take this augmented matrix, now the next step, we need to convert it in the form of we need to convert in the form of echelon form to find out the rank, and based on the rank of the augmented matrix, then we can decide whether the given linear system holds solutions or like unique solution or infinite solutions or no solutions, right? So the procedure is, first we need to find out the rank of a matrix A, and then the rank of a matrix A by B. This can be done by by considering the augmented matrix A by B. A by B both are at the time they are taken. Convert the given augmented matrix in echelon form. Echelon form, you all know that the number of non-zero rows after converting it in the echelon form gives the rank of the given matrix. So first we need to convert the augmented matrix in echelon form. Then then we can get the rank of A and rank of A by B. So after getting the rank of A by B and rank of A, the first option is if both the ranks A by B and A and A by B both are equal, definitely those type of linear equations holds solutions, and we can call that these equations are always consistent. That means they always consist some solution, right? Okay. Then if suppose if R of A is not equal to R of A by B, then you can call that the system is inconsistent. That means it doesn't hold any solution. So that is the main procedure of finding out the solutions of linear system by using the matrices. In this also, in the first one, when R of A is equal to R of B, then again the two cases arises, that is equal to number of variables and not equal to, less than the number of variables, less than the number of variables. So suppose if both the augmented matrix and the coefficient matrix, both the ranks are equal and equal to the number of variables, then that type of linear equations have unique solutions. If both the ranks are equal but less than the number of variables, then that type of equations will have infinite solution. That means the solutions contain some arbitrary constant like k, and based on the value of k, the number of solutions will be varying. So in that case, the k is completely independent. That means it lies on your hand. So you can find infinite number of values for infinite number of values of substituting k value here. So in that way, if R of A is equal to R of A by B and less than the number of variables, then that holds infinite solutions. So this is the procedure of, and if both are equal and equal to the number of variables, then it is not just nothing but the unique solution. That means one and only one solution you can find for that type of linear equations. So this is a method of finding out the solutions of linear system by using matrix tools. So let us see further. If suppose in the first case, you can see that R of this rank of A is equal to rank of A by B and is equal to the number of variables, then that particular equation has unique solution. In the second case, you can see that rank of A is equal to rank of A by B, but it is less than the number of variables. That means the number of non-zero rows after reducing to echelon form will be less than the number of variables. In this case, what happens? The one of the variable we need to assume it as k to get the the values of the rest of the variables. So obviously the rest of the variables will be in the form of that k. That is why all the x, y, z, how many variables you have, that will fall in terms of k, and based on the value of k, that many type of solutions you can get. Therefore, you have infinitely many solutions if both augmented matrix and the coefficient matrix both are equal and less than the number of variables. In the third case, if rank of A is not equal to rank of A by B, then the system has no solution. So it is for the function for the linear equation to be consistent, it is necessary that both the rank of A by B and rank of A, that is augmented, and the coefficient matrix both should be equal. And if you go with one example, let us see one example here. Solve the linear system of equations. 2x plus y plus z is equal to 5, x plus y plus z is equal to 4, x minus y plus 2z is equal to 1. Now, by observing the type of linear equation, you can say that these equations falls under non-homogeneous equations, because after converting it to the matrix form, the matrix coefficient matrix A can be written as 2, 1, 1, 1, 1, 1, 1, minus 1, 2, and into the variable matrix x, y, z, and is equal to the constant matrix 5, 4, 1. And you can see that the constant matrix is not equal to 0. Therefore, this, after converting in the matrix form, it goes in the form of ax is equal to b, and which is nothing but the non-homogeneous equation, non-homogeneous equations, right? So, for this, to find out the solutions, so we have decided that these equations are non-homogeneous by observing itself. So let us see how to find out the solutions. Now you consider the augmented matrix. As I have said before, that the augmented matrix is obtained by the combination of the coefficient matrix and the constant matrix. So the constant matrix, the column is kept at the fourth and the last, and the rest of the thing is nothing but the coefficient matrix here. Now clubbed together. Now the easiest method of finding out the rank is by echelon form. You all know that the echelon form, the number of zeros from the beside the first non-zero number should be in increasing order from top to bottom. So after completing the echelon operations, no other number should be can be reduced to 0. If you are trying to reduce the non-zero numbers to 0, then you are distracting the numbers which have with a great difficulty you have reduced to 0. So that is and after the matrix is there in the echelon form, then the number of non-zero rows that are left out will give you the rank of the matrix. That is a procedure of finding out the rank by echelon form. So let us use the same procedure, as it is very easy to convert the given matrix to echelon form. Now when I clubbed this matrix, I got 3 into 4 matrix, a rectangular matrix. So let us see how to find how to convert this in the echelon form. Now, to convert this to echelon form, let us go back once again. In the first row, in the first column, that is R21 and R31, both should be first reduced to 0. So by using the first element, that is 1. So here what I did, I have shifted this R1 and R2 so that the first row element is 1 and the operations becomes very easy. So in the first row first element we have 1. So let us convert the second row first element and third row first element to 0. So here it's just nothing but R2 minus 2R1. R2 minus 2R1. R2 is nothing but 2, 1, 1, 5. And 2R1, multiply the first row with 2. So first row is just nothing but you have the first row is 1, 1, 1. So 1, 1, 1, 4. So you can write this as, after multiplying, you can write this as minus 2, minus 2, minus 2, minus 8, right? And this can be written as R2 minus 2R1. So minus 2 plus 2 both cancelled. So you are getting 0. 1 minus 2, that is minus 1. And 1 minus 2, that is nothing but minus 1. And 5 minus 8, nothing but 3, minus 3. So we have to replace the second row because we are doing the leading the operation that has done on the R2. So we have to replace the elements by whatever values you have got here. So it's just nothing but 0, minus 1, minus 1, minus 3. In the similar way, let us go for the next one. R3. R3 minus R1. R3 is nothing but 1, minus 1, 2, 1. Minus R1, that is minus 1, minus 1, minus 1, minus 4. So both are cancelled with each other, giving 0, minus 2, 1, minus 3. So these are the values. So you substitute these two here. So you are getting the third row in this manner, right? The next operation that I can do is R3 minus 2R1. R3 minus 2R1. R3, 0, minus 2, 1, minus 3. And 2R1. The second row has to be multiplied with 2. So that 0, 2, 2, 6. So that is just nothing but 0, 0, 3, 3. So the third row is also replaced in this manner. Now you can see that this the matrix whatever you have got, in this we can't change any other number to 0, because if I try to convert this -1 to 0, I should make use of the value which is there in the R1 or R3. Suppose if I use R1 number, then R21 will change from 0 to some other non-zero number. Again we'll get the question back. So here this is completely there in the echelon form, and number of non-zero rows are nothing but 3 here. So the rank of A by B is equal to A by B is 3. So the rank of A by B is 3. So here we are taking the count of number of non-zero rows. And you all know that when a row becomes a non-zero row if at least one of the element of the given row is not equal to 0. If all the elements of the given row is 0, then you can call it as a 0 row. So here the number of non-zero rows is the count of the given matrix after reducing to echelon form. Now already we are drawing a transparent line which gives the differentiation between the coefficient matrix and the augmented matrix. So if you close this the transparent line, it is 3 into 4, and which gives the rank of the augmented matrix as 3. 3, and if you close this 4 minus 3 and 3, then the rest of the for the rest of the matrix, the coefficient matrix, the rank is again 3. So the rank of the augmented matrix and coefficient matrix both are equal. So according to the theory, you can say that if both the augmented matrix and the coefficient matrix both are equal, then you can say that the system is consistent. The system is consistent. Now we are telling that we are declaring that the system has some solution. So we need to find out what is the solution is. So let us find out whether the system, because we have already declared that it is a consistent by the cases of linear equations. So let us find out the values of the variables for the linear systems. Right now, in the first row, x plus y plus z is equal to 1, and second row we have minus y minus z is equal to 3, and third row we are getting 3. And you let's go back once again. You can see that the top here, this is a x coefficient, and this is a y coefficient, and this is a z coefficient, and this is a constant. So from from bottom to top, if you come, that is a backward substitution. This is just nothing but 3z. 3z, as it is a coefficient, the equation that you can make is nothing but 3z is equal to 3. So that implies that z is equal to 1. So the value of z which we have got, we make use of in the second equation, that is minus y minus z is equal to minus 3. So here you can put the value of z and you can get the value of y. So here I got the value of z. You can see here minus y minus z is equal to 3, and from here z is equal to 1. So you substitute here minus y minus 1 is equal to 3, or minus y is equal to 4, or 4 is equal to minus 4. So two values I got it, and the two values, that is z is equal to 1 and y is equal to minus 4, have to be substituted here. So so that you can get the value of y, x value, x plus y plus z is equal to 1. That is the first equation. X plus y is nothing but minus 4. Y is nothing but minus 4. So you can write it as x minus 4, x minus 4 plus 1 is equal to 4. Right? So x is equal to 4 minus 1 plus 4, or that is nothing but 7. That is nothing but 7. So you can write it as, let us see once again the values that we are getting here. X minus 4, that is x is equal to 4 minus 4, and this is 1, this is nothing but 8. Okay, so let us see what are the values which are getting. Y is equal to minus 3, y minus 1 is equal to, z is equal to 1. Applying the value of z in 2, we get y minus 1 is equal to minus 3, minus y is equal to minus 3 plus 1, minus 3 plus 1, and y is equal to minus 2, or y is equal to 2. I mean minus y is equal to minus 2, or y is equal to 2. Substituting, we are going to get here not 7, it is 1. X is equal to 1. X is equal to 1. 1. So let us see x is equal to 1, y is equal to 2, and z is equal to 1. So you can verify this answer also, because we can check whether our answer is correct or not just by substituting whatever values you got in any one of the equation. Actually, these values holds all the three equations. So any one equation is enough to check whether our values are correct or not. Let us see what is the question is. Question is 2x plus y plus z is equal to 5. 2x plus y plus z is equal to 5. So let us consider the first equation, 2x plus y plus z is equal to 5. Okay, x is equal to 1 we have, so 2 into 1, and y is equal to 2 you have 2, and z is equal to 1. So which is the LHS, which is 2 plus 2 plus 1, and which is equal to 5. So 2 plus 2 plus 1, 5 is equal to 5. So whatever answer you are getting is correct one. So this is the facility. After finding out the solutions for linear equation, you can check yourself your answer by substituting that answer in any one of the equation. That should satisfy. So in this method, in this way, we can find out the solutions of non-homogeneous equations. So let us see one more equation, one more example of finding out the solution for non-homogeneous equations. I have taken one in 3 into 3 variable equation. Solve the system of equations. X plus 2y plus z is equal to 7. 2x minus y plus 2z is equal to 4. X plus y minus 2z is equal to minus 1. As I've said it before, that first we need to write the given matrix in, given equation in matrix form. It is just nothing but 1, 2, 1, 2, minus 1, 2, 1, 1 minus 2 is equal into, not is equal to, it's into the variable matrix, that is x, y, z is equal to the coefficient matrix 7, 4, minus 1, right? Okay. Now, I'll club this. This is a coefficient matrix. This is a variable matrix, and this one is a constant matrix. As you can see that the constant matrix is having some non-zero terms, so therefore you can say that the given linear system of equation is a non-homogeneous equation. So we can take the augmented matrix A by B. So consider the augmented matrix A by B, which consists of 1, 2, 1, 7, 2, minus 1, 2, 4, 1, 1, minus 2, 1. Right? So as in the previous case, just we'll convert that in a form of an echelon form to find out the rank. And here you can find these R21 value and R31 value can be converted to 0 by using operation R2 minus R2 gives rise to R2 minus 2R1, and R3 gives rise to R3 minus R1. So in this way you can convert these two, right? So in this way these two can be converted. So let us see what the result we are going to get it. After converting this, I can have this see R2 minus 2R1, 1, 2, 1, 7, 2, minus 1, 2, 4, 1, 1, minus 2, 1 is a given matrix. I am interchanging for my convenience sake, because first row, first element, if it is 1, then the operation becomes very easy. And the R2 minus 2R1, 2, 4, 2, 14, and minus 2, 1, minus 2, 4, both are cancelled with each other, giving 0, 5, 0, 10. So this has to be kept replaced by R2 matrix. And here also R3 minus R1, R3 minus R1. So here R3 minus R1, 1, minus 2, minus 1 has to be cancelled with minus 1, minus 2, minus 1, minus 7, which is there in the third row of our augmented matrix. So both are cancelled. So you are going to get 0, minus 1, minus 3, minus 8. So replace all these values. Still the matrix is not in the echelon form. There is a scope of R31 element can be reduced to 0 by using R2 element, that is 5. So let us see what are the operations that we can do to convert the second row of second element of third row to 0 to convert it to the echelon form, and this I can write it as R2 plus 5R3, R2 plus 5R3. So that is nothing but 0, 5, 0, 10, 0, minus 5, minus 15, minus 40, 0, 0, minus 15, minus 30. So these values have to be replaced in the fourth row. You're going to get a 0, 0, minus 15, minus 30, and you can see that here it is in perfect echelon form. Perfect echelon form. So here you can count the number of non-zero rows. You can count the number of non-zero rows. That is nothing but three non-zero rows you have. So you can say that rank of A, the coefficient matrix, is equal to 3 by looking here, and the rank of A by B, rank of A by B is also equal to 3. As both are equal, as I have said it before, the system should be consistent. That means the system has some solution. So if we are declaring that it is a consistent, we need to find out the solution. Suppose if you are getting inconsistent, there is no need to find out the solution, right? That means the system doesn't hold any common solution. Now here we have got consistent, so we'll go to find out the values of the variables which satisfies all the three equations. So from these, the last row, you can say that minus 15 is equal to minus 13. As I've said it before, that these are the coefficient of x, these are the coefficient of y, these are the coefficient of z, and these are the constants. So if you come from bottom to top, that is backward substitution, you are going to get the equation as 15z is equal to minus 15z is equal to minus 30. So it goes in 2 terms of z is equal to 2. So I got one value, z is equal to 2. So let us go to the second one. And second one, we have got that only one coefficient is there, that is 5. So 5y is equal to 10, or y is equal to 2. Again, y is also equal to 2. So x, y and z, whatever we got here, have to be substituted in the first equation, which is nothing but x minus 2y plus z is equal to 7. So let us see what you are going to get. So x plus 2y plus z is equal to 7. Substitute y is equal to 2 and z is equal to 2 here. So you are going to get it as x plus 2 into 2 plus 2 is equal to 7, or x plus 6 is equal to 7, or x is equal to 7 minus 6, or x is equal to 1. So therefore x is equal to 1, y is equal to 2, and z is equal to 2. So let us see the verification part. The value of solutions that we have got is 1, 2, 2. So let us take any one of the equation from the equation, that is x plus 2y plus z is equal to 4. First equation, to x plus 2y plus z is equal to 4. x plus 2y plus z is equal to x plus 2y plus z is equal to 7. Is equal to 7. Is equal to 7. Substitute these values. Let's see our solution is correct or not. 1 plus 2 into 2 plus 2, that is 1 plus 4 plus 3, which is nothing but 7. Obviously, LHS is equal to RHS. So in this way, even you can verify your solution whether it's consistent or not by substituting the values which we have got in any one of the three equations. So this is the easiest method of finding out the solutions of linear equations by using matrices. And this tool, it not only confined to 3 variables. You can use this matrix tools to find out solutions for n variables. So whatever may be the matrix you are getting, it may be a rectangular matrix or square matrix. In the same process we have to do, that is converting we need to consider the augmented matrix and convert it to echelon form. Once if you convert into echelon form, there itself you can find out the rank of a coefficient matrix and rank of the augmented matrix, and which gives an idea whether the solution linear equations have solutions or not. If you are getting consistent, then we need to go for the solution. Suppose if you are not getting any solution, that means both the rank of coefficient and the augmented matrix are not equal, then the system doesn't have any solution. So in this way you can you make use of matrix tools. And this is the third question. You can see that even this is also a 3 variable question. The question is x plus 9y minus z is equal to 27. Solve by using matrix tools. Okay, and the x minus 8y plus 16z is equal to 10. 2y plus 2x plus y plus 15z is equal to 37. Now in the same manner as I did for the previous case, just I am considering the augmented matrix, that is 1 9 minus 1. This is a coefficient matrix, and 1 minus 8 16, 2 1 15, and 27 10 and 37. And you can see that the constant matrix is having non-zero elements. Therefore you can say that this matrix is the linear system is non-homogeneous equation. So we'll go and we'll try to convert this in the echelon form by using the same method, that is row operations, that is R2 minus R1, R3 minus 2R1. So R2 minus R1, R3 minus 2R1. So let's see what you're going to get here. And you are getting two similar rows are there. 1 minus 1 9 minus 1 27, 0 minus 17 17 minus 17. And you can see that these two are quite similar rows. So you can cancel these two so that the rank will reduce to the rank will be less than 3. So let us see what you're going to get here. 1 9 minus 1 27, 0 minus 17 17 minus 17. And what is the rank of augmented matrix here? The rank of augmented matrix is 2, because you have only two non-zero rows here. And rank of the coefficient matrix is also equal to 2. So this is nothing but the both are equal. Again you can say that it is consistent. But the problem is that both are equal, but they are not equal to the number of variables. Here they are less than the number of variables. How many variables are there? N is equal to 3. N represents the number of variables that are there in the linear equations. Number of variables. So as these both the ranks are equal, but they are less than the number of variables, that you can say that the system will have infinite number of solutions. Why? Because you can see that there are only two equations in your hand. The values that you need to find out is 3. So it is not possible. In order to find out the 3 unknown values, minimum 3 or more than 3 equations should be there in your hand. But if it is less than 3, at least one variable you need to assume it as k, so that you can get the other values in terms of k. So here I can say that R of A, see, look here, R of A is equal to R of A by B, which is equal to 2, which is less than 3. Then the system have infinitely many solutions. So in the first row we have x plus 9y minus z is equal to 27, and second row we have 17x plus 17y is equal to minus 17. So let us assume that put z is equal to 2 here. Put z is equal to 2, an unknown value, or k. So you are going to get y is equal to minus 1 minus k, and substitute that y value, you are going to get the value of x. So x is equal to 36 minus 80, and y is equal to minus 1 minus t, and z is equal to t, as t is a real number. How many values you are assuming for t? That many solutions will be getting for the linear equations. So this is a second one. So today we have seen two problems inconsistent, that is a unique solution, and third one we have taken the consistent but having infinite solutions. Even this is also in another example, fourth example, even this is also followed in the same manner. You can see that both the ranks here are inconsistent. See, the rank of A is equal to 2, rank of A by B is equal to 3. So both are not equal to each other, therefore it is not consistent. The system is inconsistent. That means the system has no solutions. So whenever both the ranks are equal, you can able to find out whether it may be a unique solution or infinite solutions. But if both are not equal, then you can't be able to find out any solution for the linear equation. So this is how we can find out, and these are the few examples you can try, and even the answers are also there. And besides, to check it, to check your answers, and in this exercise, we have both consistent, inconsistent, and no solution questions are also there. And that's the end of the topic. That is today. That is a consistent and solutions of linear system of equations by matrix methods. Thank you all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.